Okay, so in this video we'll talk about 2-qubit gates. So let's start by reviewing what we know about single-qubit gates. So the input is a qubit, let's say in the state alpha 0, 0 plus alpha 1, 1. The single-qubit gate is a unitary transformation on this single qubit, and it outputs alpha 0 prime 0 plus alpha 1 prime 1. Okay, so what does a unitary transformation look like? It's a two-dimensional space. So in general, U is given by 2 by 2 complex matrix, let's say with entries A, B, C, D. Now, what is U dagger? U dagger is the conjugate transpose. So you take the conjugate of the complex numbers A bar, but then you transpose the matrix. So you get A bar, B bar, C bar, D bar. And the fact that this is a unitary transformation is another way of saying that U dagger times U is equal to U times U dagger is equal to the identity. And then the fact that U transforms this input into that output is just another way of saying that if you take the matrix A, B, C, D, you multiply the input, so that's alpha naught, alpha 1, that vector, you get as output the vector, which is alpha naught prime, alpha 1 prime, which is exactly the description of the output state. Okay, so what's a 2-qubit gate? It's something very similar. So now the input consists of 2 qubits. What's the state of the of these 2 qubits? Well, in general, it's a superposition over all 4 possibilities with amplitudes alpha 0, 0 through alpha 1, 1, complex numbers. The output is a similar superposition, but with different amplitudes, alpha naught naught prime through alpha 1, 1 prime. Okay, so what should this unitary transformation look like? Well, it's now a 4-dimensional space. So what U must look like is this 4-dimensional matrix with complex entries. So it might look like A, B, C, D is the first column. And then, well, I'll just put dots because I don't want to put down so many numbers. But it's just a complex matrix. It's a 4 by 4 matrix with complex entries. And it has this property that it's unitary, which means that U dagger is U dagger U is identity. And of course, what's you can read off what's U times if 0, 0. Well, if the input was 0, 0, then the output is this superposition. It picks out the first column of this matrix. So it's A 0, 0 plus B 0, 1 plus C 1, 0 plus D 1, 1. And similarly, if the input were 0, 1, that picks out the second column of the matrix, and so on. And the fact that this is a unitary transformation means that these columns are orthogonal. Okay, so let's see an example of such a 2-qubit gate. We'll start with the simplest such example that we have. It's called the C0 gate. It's one we'll use all the time. Okay, so how does the C0 gate look? Well, this is the way it's usually drawn with a dot at the first qubit, which is called the control qubit, and a plus sign at the second qubit with a line down here, and this is called the target qubit. So C0 stands for control naught. And what does it do? Well, it's easiest to describe when the inputs are basis states. So A is 0, 1, B is 0, 1. So what it does is it leaves the control bit to go through unchanged, and it flips the target bit, performs a naught on it, if and only if the control bit is 1. So what it does is it maps 0, 0 to 0, 0, 0, 1 to 0, 1, 1, 0. Now the control bit is 1, so it flips the target bit to 1, 1. And 1, 1, again, the control bit is 1, so flips the target bit. Now, of course, in general, the input is a superposition of all these four. So you might have input alpha 0, 0, 0, 0, alpha 0, 1, 0, 1, alpha 1, 0, 1, 0, alpha 1, 1, 1, 1. So what does the C0 do to it? Well, this it leaves unchanged. This again, the control bit is 0, so it leaves unchanged. Now here, the target bit is, the control bit is 1, so it flips the target bit. So for example, this one, 1, 1 gets mapped to 1, 0. And so here you'll get alpha 1, 1, 1, 0. And similarly here, the target bit gets flipped. So you'll get alpha 1, 0, 1, 1. Okay, last thing we need to verify is that the C0 is unitary. Okay, so what's C0 dagger? Well, it's easy to see that it's just C0 itself. And that C0 dagger times C0 equal to C0 times C0 dagger, which is C0 squared. And if you apply C0 twice, you just get the identity. You can see that from here because the control bit doesn't change, and the target bit gets flipped if the control bit is 1, but if you apply twice, it gets flipped twice, and so you get back the identity. Okay, now let's go on and look at something very interesting. There are other ways we can create unitary transformations on 2 qubits. So what we could do is, we have our 2 qubits, and we could apply a single qubit gate to the first qubit and a single qubit gate to the second qubit. So for instance, we might apply Z on the first qubit and H, the Hadamard, on the second qubit. Okay, so what we might want to understand is, what's the unitary transformation that results if we apply these gates? Or in other words, if we put this inside a box, and if we call this a 2-qubit gate, what is the 2-qubit gate? What's the 4x4 linear transformation, the unitary transformation that represents this? Right? Because we know that on this qubit we are applying this transformation, and on this qubit we are applying this transformation. But we want to know what's the 4x4 unitary that describes what's happening to both qubits together. So sometimes it's easier to solve such a question if you work in full generality. So let's say that on the first qubit, we applied a transformation. So let's say we applied U1 on the first qubit, U2 to the second qubit, and let's say U1 was A, B, C, D, and U2 was E, F, G, H. So what we want to understand is, what's U, the transformation that we affected on the 2 qubits together? Well, the answer is pretty elegant. It's this. Here's how you describe it. So what you do is, imagine that, so these 4 numbers are just going to be E, F, G, H, except that they'll be scaled by A. So this number would be A times E, that number would be A times G, A times F, A times H. And similarly, these 4 numbers would be E, F, G, H, except they'd be scaled by C. And these 4 numbers would be, again, E, F, G, H, except they'd be scaled by B, E, F, G, H, scaled by D. Okay, so let's try to understand a little bit where this came from. So let's remember how the rows and columns are numbered. So this is 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so if you were labeling it by first bit alone, then the first bit is 0 here, 1 down here, and 0 to the left, 1 to the right. So with respect to the first bit, it's as though this is the, it's a 2 by 2 matrix. It looks like A, B, C, D. That's what we put down here, A, B, C, D. And now what about the second qubit? How does it look? Well, when you fix the first qubit to be 0, then this is where the second qubit, the matrix on the second qubit, shows up. It's E, F, G, H, and that's what we did. We have 4 copies of that. We reproduced that matrix 4 times, and we multiplied it by the corresponding entries. So now, okay, so it makes sense at some level, but why does it work? Well, so let's try to understand. So let's try to understand, for example, so let's see. So if we were looking at what U1 does to 0, right? So what happens to the first qubit if the input is 0? Well, you get A0 plus B1. And now let's look at what happens, what U2 does to 0. So U2, 0 equal to E0 plus F1. Okay, so now if you want to know what happens to 0, 0 when you apply U1 and U2 to it, when you apply U1 to the first qubit and U2 to the second qubit, what you get is A0 plus B1 times E0 plus F1, which is, so what's the amplitude of 0, 0? It's AE, which is exactly what we're saying here. 0, 0 goes to 0, 0 with amplitude AE. With what amplitude does it go to 0, 1? AF 0, 1, which is exactly what we are saying here. It goes to 0, 1 with amplitude AF, right? Because we'd be reading off this first column. And similarly, we can ask, what about 0, 1? Where does it go to under this mapping? So now we've got to figure out what's U2 of 1. U2 of 1 is G0 plus H1, reading off this column of U2. And so what happens if we apply U1 to the first qubit? If the first qubit is 0 and the second qubit is 1, we apply U1 to the first qubit, U2 to the second qubit, we get A0 plus B1 times G0 plus H1. And you can see that therefore 0, 1 gets mapped to 0, 0 with amplitude A times G, which is as it is here. And it gets mapped to 0, 1 with amplitude A times H, which is exactly what we had here. Right, so as you can see, what we are picking up is 0 gets mapped to 0 with amplitude A from here, and then the second 0 gets mapped to 0 or 1, or 1 gets mapped to 0, 1 with amplitudes E, F, G, H, which is what we are picking up from here. And so we get to multiply those, and so we get A times E, F, G, H as we wanted. Okay, so what does this tell us about this particular case that we started with, where the first U1 is Z and U2 is H? Well, you can just read it off. So the unitary transformation should be what? Well, it should be 1 over square root 2, 1 over square root 2, 1 over square root 2, minus 1 over square root 2, 0, 0, and then we multiply by minus 1. So we get minus 1 over square root 2, minus 1 over square root 2, minus 1 over square root 2, 1 over square root 2. So make sure you understand this, right? So where did we get it from? We got it from here. The entries of Z were A, B, C, D. So 1, 0, 0, minus 1. And the entries of H were E, F, G, H. And so we got E, F, G, H. And then minus E, minus F, minus G, minus H. Okay. So now let's spend a few minutes talking about the formalism behind all this. So let's talk about tensor products. Okay, so some of you may have wondered about this. So what did we do so far? Well, we said when we have a single qubit, here's our atom, here's the electron. It's either in the ground state, which we called 0, excited state, which we called 1. And then the state of the system is alpha 0, 0 plus alpha 1, 1, which is an element of a two-dimensional complex Hilbert space, complex vector space, which you call a Hilbert space. And then let's say we have a second such qubit. And of course, its state by itself would be in, if it was a single qubit, it would be in some superposition of ground and excited states. So it would be in state beta 0, 0 plus beta 1, 1, which is also an element of C2. So let's call this Hilbert space H1. Let's call this Hilbert space H2. So these are two qubits. But then we said something interesting. We said, well, if we were to put these two systems together, then where does the state live? We said, well, it lives in a four-dimensional complex vector space. So the amplitude is alpha 0, 0, 0, 0 plus alpha 0, 1, 0, 1 plus alpha 1, 0, 1, 0 plus alpha 1, 1, 1, 1. So there are four different dimensions. Sits in C4. Let's call this Hilbert space H. Now you might wonder, what did we do? How did we glue these two vector spaces together? A two-dimensional vector space and a two-dimensional vector space, and we glued them together in some way to get this four-dimensional vector space. How did we do this? So this is this operation of tensor product. So what we did is we said, behind the scenes, formally what we were doing was we were taking a tensor product of this vector space H1 with the vector space H2 to get a vector space H. And when we do this, the dimensions of these vector spaces multiply, and so we got 2 times 2 equal to 4. Okay, so what's this operation formally? So what this operation consists of formally is, if you have a vector u in H1 and a vector v in H2, then for every such pair of vectors, you can write down a vector u tensor v in H. Now this tensor product satisfies a few properties. So for example, it's bilinear, so meaning that if you look at u1 plus u2 and v, then you'll get u1 plus u2 tensor v here. And this is equal to u1 tensor v plus u2 tensor v. Okay, and same thing holds if you look at u v1 plus v2, you get the same sort of thing, right? You get the same sort of linearity. So now this is exactly what we did with these basis vectors 0 and 1. So what we said was, if we start with 0 here and 0 here, then the corresponding vector that we have here is 0 tensor 0, which we also call 0, 0 or 0, 0 in ket. Okay, depending upon how lazy we are, we'll either write the tensor sign or forget the tensor sign, or just run the two symbols together. And similarly, if it's 0, 1, the corresponding entry here is 0 tensor 1. Okay, this is just notation. This is just saying we are too lazy to write this out, and we'll call it that. We'll identify it with that. And similarly, 1, 0, 1, 1. Now we have 1, 0, 1, 1. You can fill in the rest. Okay, so when we put together these two Hilbert spaces or vector spaces of dimension 2, we are taking their tensor product, and when we take tensor products, we have of course, these product vectors, which are called elementary tensors, where we take a vector from the one space and a vector from the other space, and we get this product vector. But of course, this is a vector space here, so we can take all possible linear combinations of these vectors. And as we saw, when we take these linear combinations, many of the vectors we get can no longer be written as a product of vectors in the two spaces. These are the entangled states. Okay, so one last property I should mention. So the one last property is that if you look at vectors u1, v1, tensor v1, and u2, tensor v2. Now, remember these were Hilbert spaces, so we had the notion of inner product between vectors. So when we take the tensor product of two vector spaces, we've defined the vectors in this new vector space H, but what kind of inner product does it have? Well, so it inherits the inner product from H1 and H2 in the sense that for elementary tensors u1, v1, u2, v2, the inner product between these two is just the inner product between u1, u2 times the inner product between v1 and v2. And then once you've defined the inner product for your elementary tensors, then you can define the inner product for any vector in H just by linearity. So any vector in H is a linear combination of elementary tensors. You know how to take inner product of elementary tensors, so you can take the inner product for any vector in H. Okay, so this is what was going on behind the scenes when we said we have two qubit systems. This is what their states look like. We have an inner product. Finally, let me mention one other thing. So there's one more thing we just did, which is we said, what if you have a unitary transformation that you apply to each of two qubits? Then there's this procedure for figuring out what's the unitary transformation U that you applied to the two qubit system. So when we wrote out this unitary transformation, so if U1 was A, B, C, D, U2 was E, F, G, H, then what we are really doing is we are saying U is U1 tensor U2. We are taking the tensor product of these two operators. And as we saw, U has this very nice property that we can write it as A times, let's write it like this, A times U2, B times U2, C times U2, D times U2.